Welcome to Walks AP Tutor again. Last time we reviewed the 5 equations for 1D motion, specifically for constant acceleration. We also discussed that the same equations can be used for free fall. So we will do more examples in free fall later. My goal is to enable you guys to be able to apply these 5 equations for any type of 1D motion. So as long as you feel comfortable setting up the problem and understanding what's given and what's required, you should be able to use these equations to solve pretty much any problem. So let's do this exercise. So in this exercise, we have two cars that are moving at different speeds and acceleration. So car 1 is at a pit stop, getting her tire pressure adjusted. And car 2 is moving at a constant rate of 40 meters per second when he passes car 1. So let's set up the problem first, right? So we have car 1, right? We have C1 here, and this car initial velocity is 0 at a pit stop. And we have car 2, which is at this point in time, car 2 is moving at a constant velocity of 40 meters per second. What does this mean? This means the acceleration is 0 and this car is not accelerating, and that simplifies the problem for us. So as soon as this car 2 passes car 1 starts to accelerate from rest. So really key word here is accelerating from rest. So that means its initial velocity is 0 and acceleration is 2 meter per second square. And it's accelerating in order to be able to catch up with car 2. So as you can imagine, so at some point you have car 1 is still here, and then car 2 maybe is here, and then ultimately they will catch up with each other, right? So we have car 1, car 2, and then here is car 2. And you can imagine here, so at this point when they meet, this is the time they meet. That means they have traveled the same distance x of t, and they've also traveled for the same duration, right? So these are really important things to note. So that means the displacement x of t and the time are equal. And now you can solve the distance at which they meet as well as how long it takes car 1 to catch up with car 2. So now let's apply the equation. So for the first one, for car 1, we can use, we're given acceleration, we're given initial velocity, so we could use equation 2. So which is x of t minus x naught, this is starting position, equals v naught t plus 1/2 at squared. So what do we get? So initial position, as you all know, is starting from 0. So this is 0, initial speed is 0. So that leaves us xt equals 1/2 at squared. And if we put the acceleration value of 2, this will be just t squared as a function of time, right? Okay, and let's do the same thing for car 2. We can apply a really simple equation here, but let's use the same equation number 2 here, which is x of t minus x naught equals v naught t plus 1/2 at squared. So this car is, has initial position of 0 when it passes car 1, but it also has acceleration of 0. So that means x of t becomes v of t, which is just, constant speed, and acceleration is 0. So this means acceleration is 0. So in this case, we plug in the 40 meters per second. So this is 40t, and this is meters. This is just in meters, right? It's a position. So what do we do now? Sorry, I should have used this, subscript of x of 2. This is x of 1, x of 1, x of 1, right? So when they meet, the two cars, they have traveled the same position. So x of 1t equals x of 2t, which means t squared equals 40t. So we just need to solve this. And if you move, this to one side, equals 0. So you take time as a common, 40 minus t equals 0. This means it's like as times 0 or time 40. And this makes sense because the first time they pass each other is at time 0. And the next time they're going to meet is at time equals 40 seconds. So we've solved the time component. And now we can find the position. How far have they traveled when they meet, right? For this one, you just substitute on one of these equations, which is, let's say, x1 of t equals t squared. So x1 of, 40 seconds equals 40 square. This is in meters, right? This gives us 1,600 meter. So this is when they passed each other. So they would have traveled 1,600 meters before they passed each other, and it took them 40 seconds. This could also be expressed graphically, right? So if you assume your x-axis is time, y-axis is position, so x1 of t equals t squared. So this is, quadratic equation. So it will be a quadratic equation, something like this. And then x of 2t, this is 40t. So this is, linear equation. So that's going to go through the intercept, the origin. So they will meet they will meet at t equals 0. And the next time they meet is t equals 40 seconds. And when they meet, this is when it's 1600 meter. So this is how you solve it, and really expressing this as a function of time helps you simplify it. Now you can find the position at any point in time because you're able to express it as an equation which depends on time. So next we will do more problems on this. Keep watching. Thank you.